Welcome back to the specialized series on industrial artificial intelligence. In this episode, we'll explore principal component analysis, or PCA. Imagine your professor gives you a 500-page report and asks for the key insights by tomorrow morning. Reading every page would take hours. But what if someone could summarize the entire report into just 5 pages while keeping all the important ideas? You'd still understand the main story, but with much less effort. That's exactly what PCA does for data. It takes large datasets with many features and creates a simpler representation while preserving the most important information. Let's understand why PCA is needed. Suppose we're analyzing house prices. At first, we only have a few features: house size, number of bedrooms, and number of bathrooms. Simple enough. But real-world datasets often contain dozens or even hundreds of features. Distance to schools, distance to supermarkets, parking space, garden size, age of the house, nearby transportation, crime rates, population density, and many more. As the number of features increases, understanding the data becomes much harder. Finding patterns becomes difficult, visualizing the data becomes nearly impossible, and machine learning models often require more computation. This challenge is known as the curse of dimensionality. So how do we solve this problem? Dimensionality reduction helps in 3 important ways. First, it reduces complexity. Instead of working with hundreds of features, we can work with a much smaller set of meaningful information. Second, it helps machine learning models focus on important information rather than noise. Many datasets contain redundant features that provide similar information, while others contain noisy features that add confusion instead of value. And third, dimensionality reduction makes data easier to visualize and understand. Humans can easily understand 2-dimensional and 3-dimensional data, but visualizing 100 dimensions is practically impossible. Dimensionality reduction helps simplify data while preserving its important patterns, and that's where PCA comes in. Before we understand PCA, we need to understand one important idea: variance. Variance measures how spread out data points are. Assume 2 classrooms. In one classroom, all students are packed into a single corner. In another classroom, students are spread across the entire room. Which classroom shows more spread? The second one. In data, this spread is called variance. Low spread means low variance, high spread means high variance. And higher variance usually means there is more information to learn from. That's why variance is so important in PCA. Now let's apply this idea to data. Imagine a cloud of points on a graph. Notice that the cloud stretches more in one direction than another. PCA asks a simple question: which direction captures the most spread? It checks different possible directions and looks for the one with the highest variance. The direction with the largest spread becomes the first principal component, also known as PC1. You can think of PC1 as the direction that captures the biggest story hidden inside the data. After finding PC1, PCA searches for another direction. This second direction captures the next largest amount of variation that wasn't already captured by PC1. This becomes the second principal component, or PC2. An important rule is that PC2 must be perpendicular to PC1. This ensures that each principal component contributes new information instead of repeating information that has already been captured. Together, these principal components create a new coordinate system that better describes the data. Let's see PCA in action with a simple 3-dimensional example. Imagine we're analyzing houses using 3 features: house size, number of rooms, and house price. Each house can now be represented as a point in 3-dimensional space. When we plot all the houses, the points form a stretched cloud. Now imagine I ask you a question. If you had to summarize this entire cloud using fewer dimensions, which direction would you choose? PCA answers that question automatically. It finds the direction where the data spreads the most. This becomes the first principal component, or PC1. In many cases, PC1 captures most of the important information. Instead of describing the data using 3 dimensions, we can now describe it using fewer dimensions while preserving the overall pattern. That's the power of PCA. Of course, whenever we reduce dimensions, some information is lost. The goal is to lose as little information as possible. So how do we know whether a principal component is important? This is where explained variance comes in. Explained variance tells us how much information each principal component captures from the original dataset. Let's look at a scree plot. Notice that the first principal component, PC1, captures the largest amount of information. In this example, PC1 explains about 80% of the variance. The second principal component, PC2, explains another 15%. Together, PC1 and PC2 preserve about 95% of the original information. Now look at the remaining components. Each one contributes only a very small amount. This tells us that most of the important information is already captured by the first two principal components. That's why, in many real-world applications, we can keep only a few principal components and still preserve the overall story hidden in the data. So where is PCA used in the real world? One common application is image compression. PCA can reduce the amount of data needed to store images while preserving most of the visual details. In biology and medicine, PCA helps researchers analyze gene expression datasets that may contain thousands of measurements. And in facial recognition systems, PCA helps simplify complex facial information into a smaller set of meaningful features. Let's quickly recap everything we've learned. PCA is a dimensionality reduction technique. It helps simplify large datasets that contain many features. It works by finding directions with maximum variance. These directions become principal components. The first principal component captures the most important information. The second captures the next most important information. An explained variance tells us how much information is preserved. By keeping only the most important components, PCA reduces complexity while retaining the essential structure of the data. The next time you see a dataset with hundreds of features, remember this: PCA doesn't try to keep everything, it keeps what matters most. That's the core idea behind principal component analysis. The future of industry is intelligent. Let's build it together. Thank you for watching.